Welcome back, everyone. I want to spend a couple minutes to briefly talk about some of the algebraic properties of our double integrals over these more general regions. And to start off with, all the algebraic properties we discussed earlier for double integrals over rectangular regions are still going to apply. So that's like the constant multiple rule, the sum and difference rule, as well as some of those comparison rules for our double integrals over rectangular regions. They're still going to be true for our double integrals over general regions, but I want to add a couple more properties to that list. The first one is probably the most important one, and that's that if we think of our region D as the union of two other regions, D1 and D2, that are pretty much disjoint, meaning that they do not overlap each other except possibly on their boundary lines, then if that is the case, then we can express the double integral of our function f over our region D as the sum of two double integrals, the double integral over our first region, D1, plus the double integral over our second region, D2. And this just gives us a nice way to split our region up into several pieces if it is necessary to do so, and to know that that will not affect any of the values we get out of our computations. The next algebraic property for these double integrals over general regions is if we integrate the constant function 1, or we just integrate the differential of the area over our region D, that is always going to give us the area of our region D. And our third property, which is another comparison property, says that if our function we are going to be integrating eventually is bounded below by some minimum value little m and bounded above by some maximum value capital M for all points in our region D, then what we can see is that if we integrate all three sides of this inequality over our region D, the minimum value m times our area of our region D is going to be less than or equal to our double integral, which is going to be less than or equal to the area of our region D times that maximum value. And this is sometimes used to help to give us a lower and upper bound for our double integral if it's too difficult to compute. Alright, so I'm going to do one last example in this video that kind of illustrates how we can use this first algebraic property for double integrals over general regions. In this example, we want to express the sum of these two double integrals as a single double integral. And so how are we going to do this? Well, first we're going to have to kind of visualize the regions that we are integrating over. And so for both, we're integrating this unknown function f, and we're integrating with respect to y, and then with respect to x. So let's go ahead and graph the regions that are described by these two integrals and see if we can describe it in a simpler way using a single double integral. So the first thing we need to recognize is that both of these double integrals are type 1 integrals, which means the regions we are integrating over are going to be currently described as a curve on top and a curve on bottom between some interval of x values. And so, well, for our first integral, our uppermost or top curve is y equals x squared, which is going to look something like this, and our lower curve is y equals 0, which is our x-axis. And so that's going to be the region between y equals x squared and y equals 0 over the interval of x values between 0 and 1. And so our second double integral is going to be adding on to this. It's integrating over a different region. That region is going to be below the line y equals 2 minus x and above the line y equals 0. And so what does the line y equals 2 minus x look like? It's going to have a y-intercept of here of 2. Right, this is a y value of 1 and a slope of negative 1. So it is going to share that point of 1, 1 along with our other region's curves. But then it is going to go down and intercept the x-axis at x equals 2. And so the sum of these two double integrals is integrating over this entire region, but we can see that this region can be described using a single double integral if we treat it as a type 2 region instead. So if we think of this as a type 1 region, then we have to use two different curves to describe the top curve. That's what's going on in these different integrals. And that lower curve is still y equals 0 for both. But now, if we want to describe this as a single double integral and a type 2 region, what we have to do is think about a rightmost curve and a leftmost curve and express both of those curves as x as a function of y. So that just means we have to solve these equations for x as a function of y. So our rightmost curve or equation, y equals 2 minus x, we can add x to each side and then subtract y from each side and solve that and see that x is equal to 2 minus y. If we solve our leftmost curve's equation for x, we get x is equal to the square root of y. Technically, we get x is equal to plus or minus the square root of y, but x equals the negative square root of y will give us this curve over here, which is not what we want. So we want to use the positive solution to that equation when x is equal to the square root of y. And now we can see how to describe this region as a single type 2 region with a rightmost and leftmost curve. Our rightmost curve is x equals 2 minus y, and our leftmost curve is x equals the square root of y. And so our inner integral is going to be with respect to y. The upper limit of integration is going to be our right binding curve, which is x equals 2 minus y. Our lower limit of integration is going to be our left bounding curve for our region, which is x equals the square root of y. We're still integrating our unknown function, f. We're first going to be integrating with respect to x, and then with respect to y. And so for that outer integral's limits of integration, we have to use the y values that our region runs through, which is from 0 to 1. So we finished this example off. We have successfully re-expressed our original sum of two double integrals as a single double integral. And all it took was drawing our region using the information given from the limits of integration and re-expressing that region instead of as two type 1 regions as a single type 2 region. And so we can't take this double integral any further because we do not know our function f. This example is just to help illustrate and see how this first algebraic property for double integrals can be really, really useful. The hope is this double integral is going to require a lot less computation than these two individual double integrals that we then have to combine together.